Hey there, this is Mr. Piercy, and in this video what we're going to be taking a look at is how to identify extrema on an interval, meaning where is it going to have a minimum value and where is it going to have a maximum value. The first thing here, and I know this isn't part of your notes, but the first thing here is something that I would like you to take a look at. So if you want to add it just off to the side or just kind of follow along with the explanation that I'm going to have here. This is essentially like a warm-up exercise. State the critical numbers of the function, but I'm not sure everybody knows what a critical number is. So you've seen the definition of critical points in previous math classes, and what's the difference between a critical point and a critical number? Well, here a critical point is going to use the x and y values simultaneously, whereas the critical number is only going to state what the x value is. So what is a critical number? And it should say critical number, not a critical point here. But a function is going to have a critical number or a critical point somewhere on the x-axis as long as the derivative of the function is 0, meaning that the slope of the line is 0 at that point, or that it's undefined. So looking at the function that is being given to me, I can recognize that I'm going to have 3 points on the function that if I found its derivative, I would have something with a slope of 0 at that minimum, at this vertex of the maximum, and at the point of inflection that goes through the origin. So what are the critical numbers? Well, the critical numbers are going to be the x values where the derivative is 0 or undefined. So in this case we have 3 points where the derivative would be 0. Now what would the derivative look like? Here the derivative is going to look like something like this. Going back to what we saw with our curve sketching stuff in differentiation in Unit 2, wherever the function is decreasing, the derivative is going to be below the x-axis. So the function is decreasing, starting on the left from negative infinity up to about negative 3. So the derivative is going to be below the x-axis up until it gets to that point. And then it's going to be positive, or the function is increasing from a negative 3 to a positive 3. So the function is going to be above the x, or the derivative, I should say, is going to be above the x-axis that whole time. So it's going to have to come up, but because I have a point here where the slope has to be 0, well, if you notice, what's going to happen is that wherever the slope is 0, that's the solution, that's the root of the derivative. So I have to be able to come back down here and touch that one. And then I'm going to be able to come back up here some way. And we have to be able to go back through the x-axis here. So as we approach this value, we're going to go down and down, and then at that interval, right at the same time where the function starts going down again, so the function is decreasing again from positive 3 to positive infinity, well, that's where the derivative will be below the x-axis. So that kind of maroonish, it's not the prettiest sketch, but that is where the derivative for this particular function would be based on what I know on curve sketching. And the critical numbers, or the critical points, are all going to be related where the derivative has roots, because that's going to translate to a slope of 0 on the tangent line curve, or the tangent line to the curve of the function. So that one we would have 3 critical numbers, or 3 critical points. The critical numbers would be at negative 3, 0, and positive 3. So here, the first thing that they're talking about is just making sure that you can recognize when you're going to have a minimum or a maximum. Now, one of the things that we're talking about here is it's indicating what it's talking about. And let's highlight here. The reason why we want to be able to know where, a minimum or a maximum is going to be, and I meant to put my highlighter, is because that's where we can optimize something. Now, maybe in an Algebra 1 or a geometry class when you're talking about area, it's a very popular kind of question in geometry to say, okay, well, if you have a quadrilateral where the sides increase by 1 each time and the, height and the length decreases by 1 each time, well, you're going to have something that has a pattern that would look like this. And what you're trying to do is you're trying to find out, where do I have a quadrilateral with the maximum area? And the idea of being able to show you that is that, we would have a square. Basically, when x is equal to y, or when length is equal to width, or when base is equal to height, or whatever, that is going to give you the maximum area of a quadrilateral. Squares have the biggest area for something with a fixed perimeter. And we're going to be looking at optimization at some point soon. So that's why it's really important to be able to identify where a critical number is going to be, or where an extreme value is going to be. So taking a look at these sketches that we have here, where do I have a minimum or a maximum? Well, here the absolute, the ABS, they're talking about absolute maximum. In this case, the absolute maximum is going to be at the highest point that's defined, in this case at 4 and 5. So it's at the end point. The absolute minimum is what looks like to be the vertex at 2, 1. So that's somewhere on the interval from -1 to a +4. Here we have kind of looks like an inverted quadratic, an inverted parabola. What's the absolute max? Now, it's very tempting to say that the absolute max is going to be at 2, 5, but in this case, because the vertex is undefined, we have a hole there, there is no absolute maximum. Moving on to the absolute minimum, again, we have the overall lowest point at the end point of -1, -1. And the same thing with these two functions here. So the function on the left may be, I don't know, an exponential function as it's defined from point A to point B. The absolute max, in this case, because the absolute max is unbounded, there is no absolute maximum. Same thing with the minimum. The lowest point occurs when x is equal to a, but it's not defined there. So we cannot say that this function has an absolute max or an absolute minimum. And the last one, here what you're going to recognize is that what we have is there's a cusp on the function that we have here. So we would recognize that the cusp itself is not differentiable, but that's not what we're looking at. We're looking to see what is the absolute maximum or the minimum. In this case, the maximum occurs at that cusp. It is somewhere on the interval. And the absolute minimum, just like what we've seen in a couple of examples already, the lowest point that we go on the y-axis is at -1, but at both of those points, they are undefined, so there is no absolute minimum. So here you may need to pause the video so you can kind of write down these definitions, because I don't believe they're actually written for you in your notes. Relative extrema, points on the graph of a function where the function changes from increasing to decreasing and vice versa. So for instance, on a polynomial, you might have multiple places where a function is increasing or decreasing depending on what we have. So I could have a relative maximum here, a relative minimum here, a relative maximum here, and a relative minimum here. And a relative max and a relative min can be an absolute, but it's just kind of looking at it from where it changes from increasing to decreasing or vice versa. And the absolute extreme is the highest or lowest point on the function or on the graph for whatever interval that it's been defined for. So here you could probably work through these independently and then come back and just hit play at this point and see what I'm putting down. Approximate the coordinates of the relative extrema. So the relative extrema are just where it changes increasing to decreasing. So I have a relative minimum, which looks like about -1.5 and -6. And this is the same function that we were looking at earlier, and it looks like about +1.5 and +6 is where I'm going to have an absolute max, or I'm sorry, a relative max. And considering the domain of the function, what are the absolute extremas? Well, in this case, the function is unbounded left to right. I mean, this is looks like a 5th degree polynomial with a negative leading coefficient. And so the end behaviors of an odd degreed polynomial always go towards positive or negative infinity. The left side and right side are always going to go in opposite directions. So the range is going to be positive infinity to negative infinity. So because of the unbounded nature of the left and right sides of the graph, in this case there is not going to be an absolute minimum or maximum. Here, taking a look, this is probably a piecewise function made up of a bunch of line segments. State the coordinates of the relative extrema. So again, we're just looking to see where does it change from decreasing to increasing or increasing to decreasing, and these are the points that I was able to locate. Here, what is an absolute minimum or maximum? Now here we have a defined domain from -5 to +5. So in this case, it is possible to identify where is it going to be at its absolute lowest and where is it going to be at its absolute greatest. And in this case, I got 1, -5, and 3, 5. So based on what we're seeing so far, where can an extreme value occur? Where can we have extrema located? On the interval, at the endpoints, where are they going to be located? So I want you to pause the video and try and figure out what you would be able to put down here for an answer, and then hit play and compare what your thinking is versus what mine was. Okay, so let's see what you have, and here's mine. I'm saying extrema can occur at an endpoint or somewhere on the interval. Absolute extremes can be relative extremes. On a function, relative extrema in a neighborhood, that's where we would kind of just look at a small piece of the overall function, could also have the absolute extreme. Okay, so now we're going to look at the same functions, but we're going to restrict their domains a little bit. So for instance, this one here at -2 and +2, they're giving us our restrictions at -2 and +2. So anything that's to the right of that or to the left of this, they don't matter. We're only looking at the things that are in between. All right, so where do I have some absolute values? Where do I have its absolute lowest or greatest point? So here, the absolute min is going to be right here on the interval at about -1.5 and -6, and the absolute max is going to be here at 1.5 and +6. All right, so now we're going to change the restrictions on the domain. So let's see. Let me go ahead and clear all this stuff off and we'll just start over. So at -1 and +2, where do we have an absolute minimum or an absolute maximum? Well, the absolute minimum, the lowest point on the function in between those two dotted vertical lines that I added, the lowest point appears to be about right here. About right here at the endpoint itself. So here the absolute minimum looks like it's about -1, and I'm going to just say it's at a -3. And so the absolute maximum here, because we're still going to 2, the absolute maximum, the highest point that it achieves is still right there at about 1.5 and 6. So same idea here. You guys go ahead and try working this one out on your own. Pause the video, and then when you have your answers, click play and see what I put up. All right, so ideally you've done what I've asked you to do, and what we're looking at here is I'm going to have an absolute minimum at 1, -5, and max at 3, 5, and when I change the domain restrictions from the domain now being from -5 to a +2, the absolute minimum doesn't really change. That's still at +1 and -5, but the absolute maximum on that new interval is at -5 and a +4. So there should be 3 distinct places, ideally, that you can recognize where an extreme point, a relative or a maximum, or an absolute, is going to be located. And here are the 3 places that you can have it. Somewhere on the interval, whether it's at the end point or in between the 2 endpoints on the interval itself, wherever the derivative is 0, so that's where we have our horizontal line, our horizontal tangent line, or the root of the derivative, and where the derivative doesn't exist. Although the third point, that third one, we haven't really seen really much in the way of an example of that, because you really don't see that. Where f prime doesn't exist, that's really going to be like if I have a vertical asymptote on the derivative somewhere. So that's really what that third point is. And there we go. So let's go here. All right. So earlier we talked about the definition of a critical number. So here's another place where we have the definition. Now, why do we need to be able to locate those critical numbers? That's where we're getting into what we're going to look at now. Is called the extreme value theorem. So we've talked about how you identify a relative extrema. Well, now we're trying to identify where am I going to have a minimum or a maximum on any given function. And that's what those skills that we were just looking at are going to allow us to do. So for instance here, let's take a look at these. The functions, what we're asking us to do, it says justify why the extreme value theorem can or cannot be applied on the given interval. Now here, let me be clear on what I'm going to be looking at for my answers. So for instance, on this one, on example 2a, 2x minus 3 over x minus 2, that rational function, I know that rational functions definitely have vertical asymptotes, generally speaking, and this one is a very simple standard rational function that will absolutely have a vertical asymptote at x is equal to a +2. So I am definitely not continuous at x is equal to a +2. Now, in earlier lessons, when we were talking about continuity, in order to justify whether something was continuous, because that's what the question was asking, is the function continuous? Or you had to be able to show continuity for something. You had to be able to justify that continuity existed by showing that the limit existed and it was defined at that same point. Well, here we're not being asked to show continuity. We're using continuity, but that's not what we're being asked to prove. We're being asked to justify whether the extreme value theorem is going to apply. So I'm not going to go through the whole process of explaining or justifying whether or not the function is going to be continuous. Would it be bad if I showed that the limit doesn't exist at x is equal to a +2? No, it would absolutely not. Is it going to hurt you if you had it? Absolutely not. But in this case, I'm simply going to be able to explain that The extreme value theorem cannot be applied to this rational function on the given domain because it is not going to be continuous at some point on that domain. In this point, x is equal to 2. And so here we're going to look at the next one. And I would encourage you to try and make your determination here before I put the answer up on the screen for you. And so again, I'm going to be looking at this as an exponential function that has been translated 2 spaces to the right and 1 space up. And what I know about the domain of rational functions, of exponential functions, is that they're continuous over all real numbers. So in this case, the extreme value theorem should be applicable on the interval from -5 to +5. All right, looking at this third one here, again, I have a radical equation or a radical function. And radical functions are one of the types of functions that is not going to have a domain of all real numbers. It's going to be anything that has, especially because this one is a square root function, anything that's going to be greater than 0. So in this case, the overall function itself is not going to be continuous over all real numbers, and we're including some negative numbers there. So looking at the radicand, setting it to be greater than 0, that shows you that the domain is going to be all numbers that are greater than or equal to a -2. So anything that's greater than or equal to a -2 will produce a positive value that we take the square root of. But that -6 is definitely not going to be part of that domain. So in this case, the function is not going to apply because it's only going to be continuous where x is going to be greater than -2. Now, this is where we're getting into the actual meat of the lesson. This is really what we're going to be testing you on and making sure that you understand. Here we have a given function, and what you're being asked to do is to identify where will the function have its minimum and or maximum values. And so that's what we're going to look at here. So we've established that the critical numbers are located where the domain, or where the derivative is 0, where the derivative is going to have a horizontal line tangent to the curve, or you can think of it as wherever the derivative has its roots. Okay? So the first thing I want to do with this particular function is I want to get its derivative. So I'm going to go ahead and find the derivative. F prime of x, in this case, will give me 24x squared using the power rule of the derivative, minus 6x minus 9. And I want to be able to try to factor that or use a quadratic formula or something. This one is factorable. First thing I'm going to do is I'm going to factor out a 3 as a common factor, and that'll give me 8x squared minus 2x minus 3. And if I continue factoring in this case, and again, really, that quadratic, I really wouldn't spend a lot of time. If you're having a hard time factoring it, I would just go to the quadratic formula. But in this case, it would be 4x minus 3 times 2x plus 1. So that would give me a root at x is equal to a positive 3/4 on the derivative, and a root on the derivative of x is equal to a negative 1/2. Okay, so what we're going to do is we're going to do something that's referred to as a candidate's test. The candidate's test is only going to look at the possible values that would have an extreme point. So we've established that it can be somewhere along the interval but it could also be the endpoints themselves. So what I'm going to do is I'm going to take the endpoints of the interval, and I'm going to take the roots of the derivative. Those are the 4 critical points that I could have a root at, or I'm sorry, an extreme point at. And what I'm going to do is I'm going to take those numbers, and I'm going to take those numbers, and I'm going to put them back into the original function and see what do we get. So the overall smallest number, or the most negative, is -1. I have -1/2. I have a positive 3/4, and I have a positive 2. Okay? So what we're going to do is we're going to take those and we're going to plug those into f of x. So these are your x numbers that you're going to plug into the given function. Now here I would just tell you to use a calculator to figure out the numbers, because particularly for the 1/2 and the 3/4, they're not going to be particularly nice numbers all the time. So at -1, if you substitute the -1 into the given function, you'll get a return of 0. -1/2 would be 4.75. -3 or positive 3/4 would be about -3.063, and at positive 2 we were going to get a 36. Okay? So what we're being asked to do is identify what are the critical numbers? Where am I going to have a minimum and a maximum? So in this case, I would have, and let me pick a different color here to differentiate what I'm doing. So here, this is where my final answer is going to be. I'm going to have a minimum value at this point here, because that's when y goes its furthest down. So I'm going to have a minimum value when x is, and we'll do it as 0.75, I guess, since the answer I wrote out as a decimal, -3.063. Or you can just say when x is equal to 3/4, depending on what you're asked to identify. Are you giving a point, or are you just giving a critical number? And the maximum value in this case is going to be this guy right here. It goes highest up on the y-axis to be a positive 36. So here I would say 2 and 36 for a critical point, or as just a critical number, I would say when x is equal to 2, that's when I will have my maximum value for the function. Okay? So, moving on to the next one. This one, I would like you to see if you could work it out, but I know because of the derivative of the trig functions that some of us are going to have a difficult time remembering some of our points on the unit circle. So the interval that we're looking at is from 0 to 2 pi. So that's one complete circle on the unit circle. And the fact that we're using a trig or a function that has a trig operator in it doesn't change what we want to do. We still need to get the derivative of the function, so that way I can identify where are the roots of that derivative. So when I take the derivative of the given function, I'm going to get g prime of x to be equal to 1 minus 2 times the cosine of x. So what I'm going to do here is I need to find out, well, when is cosine of x going to be equal to 0? So I'm going to set this equal to 0, 1 minus 2 cosine of x, and this is going to give me, when moving the 1 over and dividing by a -2, I'm going to get 1/2 to be equal to cosine of x. So here what we're going to do is, see what are the x values that would produce something of 1/2 on the unit circle. And in this case, we are going to get when x is equal to pi over 3 radians, and when x is equal to 5 pi over 3 radians. Okay? This is all based off of, properties of the derivatives, and you really, if you have your unit circle memorized, you don't need a calculator to try and figure this stuff out. Okay, so now what are the values that we're going to use for the candidates test? Well, I'm going to use the endpoints, and I'm going to use whatever solutions that the derivative had. So I'm going to take those numbers, and let's go ahead and put them in order from smallest to largest. So I have 0, so here I'm doing my candidates test. So 0, pi over 3 is the next smallest number, and then 5 pi over 3, and then finally 2 pi. And of course, these are your x numbers, and this is going to be for g of x. And here again, for the candidates test, this is really where you should have a calculator to help you, because you want to see what the output values are going to be. So here, when x is 0, both sine of 0 and x equals 0 is going to give you a 0. So this gives you an output of 0. At pi over 3, I'm getting negative 0.685. At 5 pi over 3, I'm getting a positive 6.968 on my calculator. And at 2 pi, I'm getting a positive 6.283. And so what we're trying to identify again is where do I have the minimums and the maximums. So the overall smallest number on the y-axis is right here. So I'm going to have my minimum, as if I wrote it as a point, I would say pi over 3 and negative 0.685. If I just want the critical number, I would say I'm going to have a minimum when x is equal to pi over 3. For the maximum, here the biggest number is going to occur at 5 pi over 3. And so as a point, I could say 5 pi over 3 and 6.968. Or if I just look for the critical number, I can say I'm going to have a maximum on this particular function when x is equal to 5 pi over 3. So moving on, the next one is going to definitely challenge you as far as your trig stuff is concerned. Here, this is the one problem that they're specifically saying the calculator should be active throughout the entire problem. And let's see what we get here. Okay. So here, I'm not going to write everything out because I happen to have this one typed up. So first thing, again, find the derivative of function h. So the derivative here, the derivative of sine squared of x is going to be 2 sine of x times cosine of x. And the derivative of negative cosine is going to be negative sine, so the double negatives give me a positive sine of x. Okay? Now this is where we want to make sure that we can kind of understand the values again on the unit circle. Same thing like I've done with the very first problem where it was just a polynomial. I'm still going to set the derivative equal to 0. But at the same time, I'm recognizing that in that first row that I have typed up, that sine of x is a common factor, so I'm going to factor that out. And now I have the function in completely factored form, so I'm going to set each factor equal to 0. Sine of x is equal to 0. And 2 sine of x plus 1 is equal to 0. Now, here you have to recognize that for sine of x, you're going to have an output of 0 when x is 0 and when x is at pi. There's more than one places. That's that, cyclical nature of the outputs that you get for that. Same thing with this one. When you solve for cosine of x, you're going to get cosine of x to be equal to negative 1/2. So again, you're looking to see where on the unit circle am I going to get an output of a negative 1/2. What input numbers do I have? And that's going to be 2 pi over 3 and 4 pi over 3. So we have the two endpoints that were given to us for our closed interval, and we got solutions of 0, pi, 2 pi over 3, and 4 pi over 3 for the derivative. Now the 0 is repeating, but that still means that we have 5 numbers that we're going to be looking at for our candidates test. So I have 0, 2 pi over 3 pi, and 4 pi over 3, and finally 3 pi over 2. Now please understand, look at your decimal, or look at your fractions. 4 pi over 3, that would be like 1.3 repeating pi, and 3 pi over 2 is 1.5. So 3 pi over 2 is actually the biggest number. Don't lose track of what your biggest fractions are. So where do I have my minimums and maximums? I have a minimum when x is equal to 0 and y will be equal to a negative 1. And at 1.25, I'm actually going to have 2 places that produce a maximum. And this is partly why I'm not writing them out as an ordered pair. I'm going to have a maximum value at x is equal to, and here I really should be saying I'm going to have I typed that up probably different than how I was explaining the other answers. Where am I going to have a minimum? I'm going to have a minimum when x is equal to 0, and the output is going to be negative 1, but I'm also going to have a maximum value at 2 different places, and the maximum output is going to be at 1.25. Okay. So this one here, guys, this is going to be the last really easy problem that you're going to be seeing, and I definitely want you to pause the video and work this one out. This one's identical, essentially, to the very first problem that we had. This is just a polynomial. So work this one out and see what you get. Okay. So hopefully you've paused the video, worked out, and you have your answers, and hopefully this is the places that you're going to have a minimum and a maximum. So the smallest it goes is negative 31.25, and the highest it goes is a positive 175. So what did we do to get that number? We took the derivative, and then we set it equal to 0 and solved for x. So here I'm factoring out a 2 as a common factor, and the quadratic that's inside the parentheses can be factored to be 3x plus 7 and a 2x minus 3. Now again, the quadratic in the parentheses, that's 6x squared. If you have a difficult time factoring quadratics when a is greater than 1, just go to the quadratic formula if you need to. It's going to be quicker. So here I'm going to have solutions of a negative 7 over 3 for the derivative and a positive 3 over 2. Now here's the thing, is that the negative 7 over 3 is not going to be inside of the defined of the closed interval. The closed interval goes from 0 to 4. And so any negative numbers like the 7/3 can't be used. So it's outside of the domain, or outside of the defined interval, however you want to think of it as. So I'm going to be looking at only 3 numbers for my candidates test, the 0, the 3 over 2, and the 4, and see what we get. And those are how we're establishing what the minimum and maximum values are going to be. So the next one here, F and H. F is really testing you on your understanding of log functions. So generally speaking, a log function can't have anything that's going to be a negative number as an input, because you can't take the logarithm of a negative number. It's outside of the domain of a logarithm. So based off whatever transformations that you would have, if you move it, horizontally, left or right, that can affect the domain, because we're just looking to see where am I going to have problem or numbers that will give me a positive value that I can take the logarithm of. Well, if I look at the function that's given to me, the x squared plus minus 9, we need to know that what are the x numbers that are going to be giving you a positive value. And this one, I think, is going to be something that we want to take a look at on a graph. So I'm going to, I want to go to the calculator. Okay, let's go to the calculator. And Why aren't you? All right, I'm going to pause the video for a second. Okay, here, this is what I was trying to do on the calculator. We're just looking at the function logarithm, natural log of x squared minus 9. And what we're going to recognize is that, if you took the quadratic in the middle and you solved it for x, you're going to get a positive and negative 3 for the, solutions or whatever. So for the logarithm, anything between the negative 3 or from the negative 3 to the positive 3, if I took those and I plugged them into the problem, I'm going to get something that's not going to give me a positive value. So, for instance, if you took negative 2 and you plugged it in here, that's going to give you negative 2 squared. That'll give you a positive 4, but positive 4 minus 9 is still negative, and I can't take the logarithm of it. So everything between the negative 3 and the positive 3 are going to be excluded from the domain of this particular logarithm. And the question that we're being asked to identify is it, where are the extreme values going to be between negative 2 and a positive 5? And in this case, the function is not going to be continuous. It's undefined from negative 3 to positive 3, so it's not going to be continuous on the defined interval that we have. Now the last one that we're looking at here, this one is a real tricky one, okay? And again, real quick, let me just pause the video and I'll add this one to the graph just so you can see it. Okay, this is what I was wanting to put on the graph, and for some reason I had to put it in the form of an exponent rather than a cube root. I don't know, it's just the calculator didn't want to work for me that way. So this is what the graph of the cube root of x minus 2 quantity squared is going to be. Now, if you look at it, first of all, because it's going to be a cube root, the cube root of or the domain of a cube root is going to be all real numbers. However, here, if you notice, at 2, this is where we're going to have, maybe something that's not differentiable, okay? And looking at the function itself, so let's go back and take a look at the function. All right, well, what are we going to do with this one? Well, we hear that the interval that they're giving us is from 1 to 10, okay, that's fine. So let's do what we had been doing. Let's, I take the derivative. So here, again, I want to put it in standard, I want to put it in exponential form because that's going to be the easiest way to use the power rule. And so when I do that, I'm going to wind up with a derivative of 2 over 3 times the cube root of x minus 2. Now looking at let me go ahead and pause the video real quick one more time. Let me try adding that function to the calculator. Okay, so adding the derivative was successful here, and what you're seeing on the screen is, again, kind of showing you what this is going to look like. Now, algebraically, what we would look at is we would just say, okay, well, we would take the given radicand, whatever it is, and we would say, okay, well, where is that going to give me a 0? And that's why things are looking like the way they do at the positive 2. So the function that was given to us is continuous over all real numbers, just like every other cube root function is. But because of that quantity squared under the radicand, we're going to get kind of that cusp at x is equal to 2. And we understand that that one's not going to be differentiable at that point. So coming back to the actual problem, well, what do we see? Well, this is going to tell us that because of the domain or because of the derivative that we have, okay, in this case, h isn't going to be able to equal to 0, okay, because if I try to put 0 there, like I did in the other examples, if I try to set the derivative equal to 0 and then solve for x, we're not going to get anything. And I encourage you to try it. Put 0 there and then do anything that you want to try and, solve for x. And you're always going to be multiplying by 0. So you can't solve, so x can't be 0. And the function, because the derivative is a rational expression, if x is equal to 2, then that's going to make the function undefined at that point, and that's exactly what we're seeing on the graph. So here you know that x is not going to be able to equal to 0 because we never get to 0. We have that horizontal asymptote at x is equal to 0. And at x is equal to 2, that's where the derivative is undefined because we're going to have a vertical asymptote at that point. So what does that mean for our candidates test? Well, for our candidates test, we still have to look at the endpoints. We still have to look at the 1 and the 10. But the only other thing that's on the interval that we may need to take a look at would be the value of 2. Okay, because first of all, 0 is going to be outside of the domain, or it's going to be outside of the interval. Okay, but the candidates test that we're going to look at are going to be 1, 2, and 10. And if I take those values and I substitute it back into the given function, I'm going to get outputs of 1, 0, and 4. So the coordinates where I'm going to have my minimum value at are going to be at 2, 0, and the minimum value itself is going to be 0. The maximum point, or the point that produces my maximum would be at 10, 4, and the maximum output of that case is going to be at 4. So this last example, that was kind of a beast on that one as far as understanding the properties of those types of functions and really knowing what their domains tell you about the function itself. So this is going to wrap it up for what we're looking at on Extrema. Okay, understand that extreme values or extreme points of a given function are going to be located wherever its derivative has its roots. And so that means we have to be able to find derivatives of a whole bunch of different types of problems and then be able to solve those for 0 and then perform a candidates test for the extreme value theorem to show that, oh, I'm going to have something here that's going to be a minimum value or a maximum value. And so the last thing that you need to be able to do is understand that for the extreme value theorem, the function needs to be continuous over whatever its defined interval is. All right, so we're going to end it here, guys. Thanks for watching. Be good, take care of each other, and we will see you soon.